Hello everyone. As part of the NVIDIA GTC 2020 online conference, RidgeRun is presenting the talk How to Build a Multi-Camera Media Server for AI Processing on Jetson. Myself, Carlos, and my colleague Jennifer will guide you through the main components of a media server and how to add AI features fully accelerated by the NVIDIA Jetson platforms. By the end of this presentation, you will know how to easily integrate your DeepStream models with other multimedia modules, such as video capture, video encoding, recording, or a snapshot, and even with a streaming of video. Please note that we assume that the attendee of this talk has basic knowledge about GStreamer and NVIDIA DeepStream framework. First of all, I would like to introduce our company, RidgeRun. RidgeRun is an US software-only company with more than 12 years of experience in embedded systems. We have more than 47 engineers working full-time on multimedia applications and Linux development. Our areas of expertise are 6 and include Linux development involving camera drivers, ISP drivers, and ecosystem drivers. We also work with GStreamer, as you might know. We perform GStreamer solutions for video and audio applications. We create custom elements, and we also work with our customers to optimize the performance of their GStreamer applications. In this line, we also help our customers to create custom applications and to the development of the software products for them. Also, we work on computer vision front in terms of image analysis, CUDA development, and GPU algorithms for custom solutions of our customers. We also work with FPGA and video-based FPGA solutions. And finally, we have very big experience on artificial intelligence with expertise on NVIDIA's DeepStream and NVIDIA's frameworks such as TensorRT and CUDA. Let's define why a media server is important. A media server provides advantages for applications, developers, and users. The features of a media server are modular, so that applying changes in one module don't affect the others. Also, the media server can be scalable. You can have one instance of the module, but you can also have 100 instances. So your application can be scalable without almost any impact on development time. The media server might or might not be isolated in a different process, so that other applications or processes, such as GUI user interfaces or user controls, can send requests to the media server using inter-process communication. Additionally, multiple features are managed by a single entity, such as the video capture, video processing, and the recording and snapshots, so that the media server has multiple advantages in your development. What about adding DeepStream to your media server? Well, you can get a whole new world of AI capabilities in order to detect or classify events and take actions based on that information of the inference result. These new capabilities generate a brand new market of intelligent products that can be used in multiple industries. For example, some use cases for the media servers could be on the surveillance front. You can have a system detecting people in your backyard, and if someone is detected in the middle of the night, a video recording or a snapshot can be triggered in order to record that person. Another example can be on the sports field. You can enable multiple video streams showing football, basketball, or soccer matches, and see players' statistics in real time to analyze their positions, movements, or any other information. So that, which are the media server modules on an AI media server? We have the cameras. We can also have the video processing and AI modules in order to perform scaling, color space conversion, and also the deep learning capabilities with DeepStream. We can also have the video encoding. You can select either VP9, VP8, H.264, H.265, or even JPEG encoding. And you can have additional features such as the recording, a snapshot, and a streaming. So, when you want to use all these modules with GStreamer, you typically build a GStreamer pipeline as shown, with all the elements and modules connected in a single pipeline, and if needed, using T elements to create branches and to perform multiple functions simultaneously. This big pipeline is created instantiating elements individually, creating GStreamer bins with elements and connecting paths as soon as you have all your bins created. But can we identify typical development problems with this approach? Well, yes, some common problems that we have identified when building GStreamer applications could be that it is not easy to implement dynamic control of the data flow in a GStreamer pipeline, and when achieved, it requires several lines of code. Also, it is hard to extend your application with new functionalities or new modules. That extension usually requires code replication on your GStreamer implementation. And also, the developers usually don't have enough time to learn how to use the GStreamer API, and that causes big implementation efforts even for simple testing or simple prototyping. What is our proposal to solve all these problems that we have identified? Well, RidgeRun has two open source projects, GStreamer Daemon and Gstinterpipe. What are they? Let's start with Gstinterpipe. Gstinterpipe comes up to answer the question how to interconnect different modules. Interpipe is an open source project designed to allow communication and interconnection between two or more pipelines. We have two elements, interpipesync and interpipesers. The interpipesync element pushes the incoming buffers to each interpipeser simultaneously. Each interpipeser has to be listening to the interpipesync node. Each interpipesync could have multiple interpipeser nodes connected, and you can connect or disconnect nodes at runtime as easy as changing the listen to property in the interpipeser's element. It is a very easy project to use in order to interconnect multiple modules, and it comes out to substitute the T element because its simplicity and managing dynamic pipeline control. Here you can see how your media server will look like when using Interpipe. You can see the video capture is connected to the video processing and AI module using GStreamer interpipes. Also, the AI processing module is connected to the video encoder through a single GStreamer interpipesync, so all the encoders modules can listen to the interpipesync on the AI module. And finally, your additional features, recording, streaming, or a snapshot, can listen to the video encoding pipelines, and you can change the pipeline that you want to receive buffers from dynamically and at any time you want. Now that we have full control over the data flow using Gstinterpipe, how can we control the media server execution dynamically and easily? Well, we can use GStreamer Daemon. GStreamer Daemon is a RidgeRun open source project which provides dynamic pipeline management. Basically, GstD works as a server that manages all the GStreamer logic and implementation internally, and its clients can send commands to run operations like parent state controls and elements properties controls in a user-friendly way. GstD works as an abstraction layer in the top of GStreamer and provides a GSD launch-like command line interface. You can have a Python or C++ client in your application controlling the GStreamer pipeline externally and receiving commands from user interfaces that are converted into GstD commands underneath. So developers don't worry about the GStreamer API implementation. Here you can see the typical architecture of a GStreamer Daemon application. GstD interacts with GStreamer directly, and there are multiple clients that uses the inter-process communication in order to send commands to GstD and requesting to create, delete, stop pipelines. You can also change the state of each pipeline, or you can request to change or to read the properties of specific elements in your GStreamer pipelines. Now that we know two very useful tools, let's see how to build an AI media server in 30 minutes. Of course, we are going to use GStreamer, our main framework, and we will use GStreamer Daemon and Gstinterpipe. DeepStream will be our main AI module to provide the deep learning features, and we will use the hardware accelerated plugins provided by NVIDIA in terms of encoding and decoding. We will use Python, but we are not limited to it. We can use C, C++, and in case the developer wants to use a different programming language, we will also use a Jetson board, of course, and we can run the media server on Jetson Nano, Jetson TX1, TX2, or even GStreamer based, depending on the capabilities that you want to achieve. And finally, in order to capture video and to get the video feed, we will use cameras. As part of this media server, we will use two cameras, one USB camera and one MIPI camera. So this is how our media server will look like. We have video capture module, video processing and AI module, our video encoding module, and the additional features involving recording, streaming, and snapshot. We will introduce each module independently, starting by the video capture module. Let's start with the video capture module. In Jetson platforms, you have three interfaces available to capture video. The first one is the MIPI CSI interface, which is very common within customers and they typically use it on their applications. You can choose from multiple sensors manufacturers like Sony, OmniVision, or OnSemi. Another interface is the USB interface, which is the most easy interface to use. And the third interface is the SLVS interface that is only available on the Xavier platforms in terms of hardware and software support. Additionally, you can have GMSL 1, 2, or FPD-LINK III to MIPI converters, which allow you to have your cameras and sensors up to 15 meters distance from the Jetson board. When building media servers, a typical configuration is to have video streams from multiple cameras working simultaneously, and you need special hardware and software to get support for multiple cameras on Jetson platforms. For example, RidgeRun and D3 Engineering have an FPD-LINK solution with support for up to 16 cameras, running on a Xavier board using the D3 hardware design, as you can see in this image, and the RidgeRun software in terms of camera drivers and also on application side. You can check out our demo wiki page on the following link. Here you can see how the camera pipelines in the media server will look like. First of all, you need to instantiate a GStreamer demo client and create the pipeline. The syntax to do so is as follows. The client has a pipeline create function which requires two parameters: the pipeline name, in this case camera 0, and the full pipeline description. We have two video capture pipelines using two different capture interfaces. The first one using B4L2 source and the B4L2 interface, mainly using USB cameras. It uses the B4L2 source element, which is included in the default GStreamer distribution. And the second one is using NVIDIA camera source, which is the NVIDIA's video capture GStreamer proprietary element, which uses libArgus underneath to control the video flow, change capture parameters, and enable the ISP processing on the Jetson platform. You can see that both pipelines use the Interpipe sync element, so any additional module could listen to this node in order to get video coming directly from the camera. The name of each node should be different in order to identify each pipeline and each node. The next module in the list is the video processing module. This module is intended to provide all the required features to operate over the video stream in order to change it to be processed and consumed by the following components. Typically, this module is useful to convert the video stream from the format given by the camera to the format accepted by the encoding or AI modules in terms of color space conversion, frame rate control, resolution, and in case of Jetson boards, it is important to control the memory conversions and memory management in order to convert to and from NVMe memory. One critical feature in this module is the usage of hardware accelerated plugins. In the Jetson board, we can use the NVVidCon or NVVideo convert elements to perform the video processing functionalities fully optimized by hardware acceleration. Here you can see the video processing pipelines. First of all, you can see that we are using the Interpipe source elements listening to the video capture nodes, camera 0 and camera 1. The camera 0, coming from the USB camera, provides video frames in 720p and YUY2 format. So we use the NVVideo convert element to perform two conversions: format conversion to RGBA and memory conversion to NVMe. On the other hand, camera 1, coming from NVIDIA's camera source, provides video frames in 720p and I420 video format, so the same format and memory conversion are needed on this branch. These formats conversions are needed because DeepStream, which is the following module, requires that specific format to operate successfully. Finally, we added the Interpipe sync element, which will become the point of contact for the following modules to obtain video frames processed by the video processing module. These new nodes have new names: camera 0 RGB A NVMe and camera 1 RGBA NVMe. The next module in our media server is DeepStream. I won't go deeper on this one, and as you may know, DeepStream is an NVIDIA framework for performing deep learning inference built as a GStreamer project with several elements with independent features, making use of TensorRT engine fully optimized for NVIDIA hardware. Here you can see some of the DeepStream GStreamer elements. In our media server, we will use all of them. The NVIDIA MUX element is very useful to batch multiple images coming from multiple video sources. In this case, we will use a batching of 4 cameras. Then we have the NVInfer element, which runs the inference engine and can be configured in primary or secondary mode, depending on the number of AI models running in your application. Our media server will use only one as primary, and we'll use the ResNet 10 object detector shipped with DeepStream as example. Finally, we have the NV Tracker, NV Multistream Tiler, and the NV DS OSD to perform tracking, formatting, and overlay functions on the video frames processed. Here you can see how the DeepStream pipeline will look like. First, the Interpipe source elements listening to 2 cameras introduced before, Cam 0 and Cam 1, going to 4 inputs in the NVIDIA MUX element running the batching mechanism. The output of the NVIDIA MUX element goes to the NVInfer and the rest of the DeepStream elements, to finally end up in the interpiping node, to which further modules can start listening to get the video frames with the inference information attached.
Now that we have a video with the DeepStream insights, we want to compress it in order to use it later for recording, streaming, and snapshots. This way, our recordings and snapshots won't take too much space, and the streaming won't overload the network. This is very important in embedded systems, given that usually the amount of available resources is small compared with other systems, and it's necessary to manage these resources as well as limit the power consumption in some cases. To achieve video compression on the video stream, we perform encoding. GStreamer provides elements for encoding. However, before we choose which encoder to use, we have to take into account potential issues. Video encoding is a computationally intensive task that can lead to a high load on the CPU, especially if it's performed by purely software. This is the case of the GStreamer encoders by software. A CPU with a high load can lead to bottlenecks in the pipeline, and these cause low frame rates or loss of quality in the video stream. To avoid these bottlenecks, we can leverage on the available hardware and software to accelerate the encoding process. NVIDIA Xavier provides a hardware codec that allows us to perform encoding and decoding on the hardware codec, leaving the CPU and the GPU bandwidth available for other tasks, such as computer vision or artificial intelligence. The GStreamer plugin that allows us to take advantage of the hardware codec is called GstD for Linux 2. This plugin provides encoders for H.264, H.265, VP8, and VP9. In the Xavier board, the VP8 encoder is not supported yet. Then, our media server will use the other 3 available encoders. NVIDIA also offers a proprietary plugin to encode and decode JPEG. We will be using the NVJPEG encode element to encode our media server snapshots. These are 2 examples of encoder pipelines. The top pipeline is used for VP9 encoding, while the bottom pipeline is used for JPEG encoding. Notice that we use the JPEG codec name as the pipeline name and the VP9 for the VP9 pipeline, so that it will be easier for us to refer to these pipelines later. Note that the interpipe source elements of both pipelines have their listen to property set to the DeepStream Interpipe sink name. In this case, the name that was designated for this interpipe sink was deep. Now, the buffers have to go through a NV video convert to change the input video color space so that the encoders can understand the input buffers. After format conversion, we can finally compress the video. For the VP9 pipeline, we use a hardware accelerated element called NVIDIA for Linux VP9 encoder. And in the case of JPEG, we use the NVJPEG-ENC. Notice the property maxPerf set to true in the VP9 pipeline. This property is useful for applications that need the best performance at high resolutions and frame rates, and that can sacrifice the increased power consumption. Of course, enabling this property might not be a good idea in the cases where low power consumption is a hard requirement. Then, the encoding pipeline must be tuned for each use case individually. Finally, we have an interpipe sync element after the encoders to make available the encoded streams. Notice the name designated to these interpipe syncs. In the case of the VP9 pipeline, it's VP9 sync, and in the case of the JPEG pipeline, it's simply JPEG. Now that we have the encoded video stream, let's talk about recording. Before we can save the video to file, we need to mux it into a container. A container is a wrapper that puts together encoded streams. Some container formats accept encoded video and audio streams, and others also allow encoded metadata. GStreamer has plugins for many formats. For instance, Matroska, MP4, and Transfer Stream are often used. Here you can see a recording pipeline for H.264 at the top and for VP9 at the bottom. Notice that the interpipe source of these recording pipelines have their listen to property set to their corresponding encoded stream. In the case of the top pipeline to H.264 sync, and in the case of the bottom pipeline to VP9 sync. In the H.264 pipeline, notice that there is a parser element that is not present on the VP9 pipeline. This parser was required only for the H.264 pipeline because the output of the encoder was not directly accepted by the MUX, and we needed to adapt it to something that the MUX could understand. In this example, we muxed the encoded video stream into the Matroska container using the Matroska MUX on both cases. Finally, we use the file sync element to write the recording to file. This file sync element has a very important property called location that we will be using later for setting the location of the recording file. Now that we have the recording pipelines, let's take a look at the snapshots. The snapshots could be triggered on demand by the user or when the system detects an event. GStreamer Daemon allows us to take snapshots dynamically. This is the snapshot pipeline of the media server. Notice that its interpipe source element has the listen to property set to JPEG, which is the name of the Interpipe sink that provides the JPEG encoded video. Also, notice the non-buffers property set to 1. This will allow the first buffer that goes through the Interpipe sink to reach the file sink, and then the Interpipe source will send an end-of-stream event and no more buffers will be accepted. This is important to avoid overwriting the snapshot with more recent buffers and to ensure that the desired event is captured. Finally, the snapshot can be written to file using the file sync element. We will use the location property of the file sync to set the file name of the snapshot. At this point, we have discussed recording and snapshots. Now we will overview streaming. There are multiple protocols that can be used for streaming, such as UDP, TCP, RTSP, WebRTC, for instance. Some of the available protocols are open, others are proprietary. The chosen format depends on the use case requirements. For instance, some applications might compromise latency and quality of experience in favor of security. Scalability and data integrity are also important considerations when choosing a protocol for streaming. Two of the most used formats are WebRTC and RTSP. Both have GStreamer support. GStreamer provides the WebRTC being element. Also, RidgeRun has WebRTC products such as the GstD WebRTC plugin that converts pipelines into WebRTC compliant endpoints. WebRTC allows to stream video that can be viewed in a browser without the need of any additional web plugin. Then, is very useful in web applications. In the case of RTSP, Gstreamer provides a RTSP server that can be used to write an application on top of it. Also, you can use RidgeRun RTSP Sync proprietary element that is based on the GStreamer RTSP server and provides better flexibility, quick prototyping, and it's easier to use. Now that we have described the media server blocks and you have seen some example pipelines, we can take a deeper look at the implementation. First, assuming a fresh Jetpack 4.3 installed in your Jetson board, we are going to install GStreamer Daemon and Gstinterpipes, which are RidgeRun open source projects. For this, you can follow the instructions in the provided links. After installing those projects, you should be able to initialize GStreamer Daemon with the command shown here. The uppercase D switch can be used to prevent the GStreamer Daemon from running as a detached process. You can take a look to GSD developer page to learn more about the options to start GstD. We create a Python script named mediaserver.py to create and control the pipelines. This is the file where all the previous pipelines are contained. In this media server, we will use the GstD Python client to control our pipelines. So, we need to first import the Python GstD client. Then, we need to create the GstD client instance. This client object is what we are going to use to communicate with GstD. Also, in previous sections, we used this client to create the pipelines of the media server. Remember that each pipeline that was created in the previous section had a name and a description. That name was very important because we now can simply call the pipeline play command with the name of the pipelines, and the pipelines will start playing. In this case, we are requesting GStreamer Daemon to play the video capture pipelines and the DeepStream pipelines. Now in this section, we will overview how to control the VP9 pipelines for recording. However, these commands also apply to the pipelines of the other codecs. Now, if we want to record a video, the first thing we need to do is to specify the location where it will be written to. For this, we use the element set command. We need to set the location property of the file sync element to the desired file name. As we are using the Matroska container for our recordings, it makes sense to use the mkv extension in the file name. Notice that the element set commands take as input the pipeline name, the element name, in this case file sync, the property name, location, and the value that we want to set the property to. This value can be set to an absolute path or to a relative path. If we set the value to a relative path, the recording will be written to the directory where GstD was started, such as in this example. After this, we can play the encoding and recording pipelines using the pipeline play command. The VP9 pipeline will start receiving and encoding DeepStream output buffers. Then, the output of the VP9 encoding pipeline will be muxed and saved to file by the recording pipeline. So, at this point, we would have two cameras capturing and connected to a video processing stage that takes care of color space conversion. These buffers are used then by the DeepStream pipeline, and finally, the output of the DeepStream pipeline goes through the encoding and recording pipelines. We could have all encoders enabled at the same time, or enable only a subset of them. In our media server, we perform recording of H.264, H.265, and VP9 simultaneously. Once we have recorded the video of interest, we simply send an end-of-stream event to the encoding pipeline, so that the encoder can finalize properly. Then we can stop the encoding and recording pipelines using the pipeline stop command, with the name of the pipeline as an argument. This is important to ensure that the video file is closed properly. At this point, we can inspect our recorded videos. You should obtain a video that has the camera video capture from two cameras enhanced by the DeepStream insights. As you can see, the DeepStream pipeline will put 4 captured frames into a single frame and enclose with a labeled box the detected objects, such as in here, where a person is detected, or in this other video, where multiple cars are detected. What happens if we want to record directly from the camera output? By passing in this way the DeepStream pipeline. The dynamic nature of the interpipes allows us to change the connections. we simply change the VP9 encoding pipeline interpipe source property to the desired camera pipe interpipe sync name. In this case, the camera 2 output with the color space conversion. For making these kinds of changes to the listen to property, we use the element set command. Using the name of the encoder pipeline, the name of the interpipe source that we wish to change the property, the name of the property, and finally the name of the interpipe sync that we want to connect to. Now we set the desired file name using the location property of the file sync element in the recording pipeline using the element set command as we have seen previously. Finally, we play the encoding and the recording pipelines to begin the recording. So, at this point, we have the camera 2 with some video processing for required color space conversions. And then we have the encoders that pass these buffers to the recording pipeline to be written to file. In this way, we are bypassing the DeepStream pipeline. This example demonstrates that it is easy to change the configuration of the pipelines using interpipes and GstD. After stopping the recording as shown before, sending an end-of-stream event to the encoder pipeline, and then stopping the encoding and recording pipelines, you should be able to inspect the file and find a recording that has only the video of one camera without any additional overlay. In the case of snapshots, we also need to set the file name using the location property of the file sync element in the snapshot pipeline. Then we simply play the encoding and snapshot pipelines. Recall that originally the JPEG encoded pipeline input is connected to the DeepStream output, and the DeepStream input receives the video capture of two cameras. Then, when inspecting the result, we expect to find the DeepStream insights as in this example. The DeepStream pipeline puts each video capture into a single frame and adds an overlay with additional information. Now we can stop the JPEG pipeline. Then we connect the input of the JPEG encoder to the other source instead of the DeepStream output to take another snapshot. For instance, in here we connect to the camera 2 output by changing the listen to property of the JPEG interpipe source. Now that we also have the JPEG pipeline connected to the second camera, we wish to change the file sync location property in order to avoid overwriting the previous snapshot. Finally, we can simply set to play the encoding and snapshot pipelines. At this point, the JPEG encoder input is connected to camera 2, bypassing the DeepStream pipeline and directly into the JPEG encoder, and this JPEG encoder is connected to the snapshot pipeline that writes this to file. Then we can inspect a snapshot with only one camera information and without any DeepStream annotations.
As you can see, with a media server you can control your features pretty easily, but also You might want to have more complex scenarios and take decisions based on events triggered by the inference information and the DeepStream module, so that other processes, applications, or clients can monitor events, signals from the media server, process them, and generate actions, such as start or stop a recording, taking a snapshot, or start a streaming dynamically and automatically. For example, our media server could detect a person in a working zone where it is not allowed to be, generate an event signal, and our custom application might start a recording in order to know who is walking around there without permission, violating the safety instructions. With this complex scenario, you can do whatever you want. You can set up a set of rules in your application oriented to monitor, detect, or classify events, always depending on the custom trained AI model. And the most important point here is that the media server control and execution are not affected, and you can add or remove rules depending on your use case and the specific AI model that you are using. There is a world of possibilities when talking about scenarios for an AI media server. You can set your imagination free and design a completely autonomous system using the media server capabilities and the AI power. To summarize our presentation, let's talk about the main conclusions that we can obtain from our 30 minutes media server. First of all, RidgeRun provides easy-to-use GStreamer tools like GStreamer Daemon and Gstinterpipe in order to integrate dynamic, modular, and scalable applications. Both projects are completely open source, and you can include them in your design without any problems. There are people always improving them and working with them, so they are optimized and new features are added almost on a daily basis. Don't hesitate to give them a try. Also, NVIDIA DeepStream provides a fully optimized framework to easily integrate AI features into your application, so your application can be smarter than ever, using the huge Jetson board's capabilities. Jetson family has a wide range of solutions, so you can choose the one suitable for your case. And finally, it is important to mention that a media server configuration depends on the customer's needs and requirements, but it doesn't mean that the implementation and development will be harder or complicated. You can design your app in a modular and scalable way without looking forward for limitations on implementation and without being afraid of the GStreamer API for development stages. You can find more information in our website. You can learn about our working models, our products and services, areas of expertise, and ongoing projects, and more. You can also review and test the media server that we have introduced in this presentation in our wiki page, which contains the media server code, examples, and the basic understanding to make it run in your Jetson platform. You can pass by our store and check out software products like GstCUDA, GstInference, and GstWebRTC, which might help you to extend the capabilities and features in your media server. Finally, in case you need further assistance, don't hesitate to contact us to our support email. We will be happy to hear your feedback about this presentation or to provide support in your application development. Thanks for your time, and we hope this talk will become very important for your company and your personal projects.